Welcome, friend. We've been waiting for you. Have a seat.
This is actually the follow-up to my first video, and here we will be discussing about nuclear energy. This video is actually a little rushed because I wanted to get it out quickly since the exam is approaching fast. Without further ado, follow me down to the world of the nucleus. Imagine that you have a generic nucleus filled with protons and neutrons. We know that particles of the same charge repel each other. And so, if you were to try to push a proton into the nucleus, then the electromagnetic force or the electrostatic force would repel this proton. But if you wasted your own energy and managed to do enough work against the electrostatic force to get the proton close to the nucleus, then at a certain distance, a force called the strong force will reach out and grab this proton. This strong force is the force that binds all the protons and neutrons together in the nucleus. You see, it can only act at very short distances, but it's much stronger than the electromagnetic force. Another interesting thing is that when the proton is finally attracted by the strong force, the nucleus will release a certain amount of energy. This means that the reaction in which a proton or a neutron is added to a nucleus is an exothermic reaction. If you are a chemistry student, then you will find it very easy to understand because you have learned that when chemical bonds are formed, energy is released. Similarly, when nuclear bonds are formed, energy is released. But where does this energy come from? To answer this question, we will first try to assemble a nucleus from scratch. For the purpose of understanding, let's assume that the mass of a proton is 10 kg and the mass of a neutron is also 10 kg. Now this is much higher than the actual value of each, but we are only doing a demonstration here, so bear with me please. So if you take a 10 kg neutron and you place it on a scale, then how much will it weigh? That's right, 10 kg. But now if you take a proton and you place it on the scale again, then how much will it weigh? 20, right? That's where you're wrong, buddy. For you see, when two nucleons, that is either protons or neutrons, are brought close together, the strong force will act to bring them together and release a certain amount of energy, and in doing so the resultant system mass will decrease. This decrease in mass is called the mass defect. Now in our example we assume that 1 kg is lost, but remember that this is just an example and we will discuss exact numbers later. So now we keep adding nucleons to our nucleus and we keep losing little bits of mass, and this adds up to what we call the mass defect or the mass loss. Alright, so finally we added 4 nucleons together and the resultant mass should be 40 kg, but it's actually 37 kg. And where did the extra mass go? The extra mass was lost. How was it lost? It was lost as the energy released when we were adding the nucleons. But how can mass be lost as energy? That is an interesting question, because you see, Einstein found that you could convert mass into energy, that mass and energy were two sides of the same coin, and he came up with the world famous equation E equals mc squared to find the energy that you could get from a certain amount of mass. So now the mass we lost was 3 kg, and if we plug this into the equation and we substitute the value of c, which is the speed of light, and as you know, the speed of light is 3 into 10 to the power 8 meters per second, we will get this answer. Now remember, when you plug the mass in as kg, you will get the energy as joules. So to recap, when a nucleon is brought close to a nucleus, it will stick to the nucleus because of the strong force, and a certain amount of energy will be released. Because of this energy release, the resultant mass of the system will be less than expected, and the lost mass is called the mass defect. If you are a chemistry student, then you will find this very easy to understand, because you already know that when chemical bonds are formed, energy is released. So similarly, when nuclear bonds are formed, energy is released. So we can understand that when any atom is formed, the mass of the atom will be less than the masses of the individual protons and neutrons. So to get the mass defect for the formation of any atom, we subtract the mass of an atom from the mass of the individual nucleons. When we substitute the mass defect into E equals mc squared, we will get the energy released in the formation. This energy is called the nuclear binding energy. This is because this is the energy that you will have to give back to the atom in order to separate all the neutrons and protons. So, if an atom released a lot of energy during formation, then you will have to give back a lot of energy to break the neutrons and protons apart. That means that an atom with a larger nuclear binding energy is actually more stable because it requires more energy to break apart. But the stability also depends on the size of the nucleus or the number of nucleons in the nucleus. So we write the expression for stability as the nuclear binding energy per nucleon of the nucleus, which is the value you get by dividing the nuclear binding energy by the number of nucleons. So remember, when the nuclear binding energy per nucleon increases, then the stability increases. If you have to compare the stability of several atoms, I suggest that you draw a table like this and enter the nuclear binding energy in the first row, the number of nucleons in the second row, and then divide row 1 by row 2 and get the nuclear binding energy per nucleon. Now in this example, you can see that even though uranium has the highest nuclear binding energy, the binding energy per nucleon is the lowest. So it is unstable compared to the other atoms. Also note that the binding energy is usually given in mega electron volts, which is another unit for energy, and you can convert it into joules from the conversion box given on the lower right. Now, a nuclear reaction is a reaction where a set of unstable reactants react to form more stable products. As the products are more stable, energy will be released in this reaction and there will be a mass defect. You can find the mass defect by first summing the mass of the reactants, then summing the mass of the products, then writing mass of reactants minus mass of products. Finally, you can plug this mass defect into E equals mc squared and get the energy released by the nuclear reaction. We will discuss an example reaction, which is the fission of uranium 235. Now this is only one of many possible reactions that uranium 235 can undergo, but this is a very common one. Now this is one of the reactions that occurs when a nuclear bomb made of uranium 235 blows up, but we will talk about it later. For now, let's calculate the energy released. Remember that the masses of the atoms will be given in atomic mass units in the question. So you sum the mass of the reactants and then you sum the mass of the products, and then you remove the mass of the products from the mass of the reactants, which will give you the mass defect in atomic mass units. But we need to convert this mass into kilograms in order to substitute it into the equation. Well, this is the relationship between an atomic mass unit and kilograms. If you have trouble with conversions, this is a handy trick that I teach people. Just divide by the unit that you want to remove and multiply by the unit that you want to convert into, which gives us this mass in kg. Finally, we can plug it into E equals mc squared and substitute the value of C, which is 3 into 10 to the power 8, which gives us the energy released by the nuclear reaction in joules. Now remember, this is only the energy for one atom of uranium. 1 mole of uranium will have a number of atoms equal to the Avogadro's constant. So the energy released by 1 mole of uranium will be the energy released by one atom times the number of atoms, which means 1 mole of uranium releases over 16,000 gigajoules of energy. As 1 mole has 235 grams of uranium, 1 gram of uranium will release 71.82 gigajoules of energy. But I know people have trouble wrapping their heads around these numbers, so we'll be doing a very common comparison. You see, people usually compare the energy released by uranium to the energy released by TNT or dynamite, as you might know it. But remember, uranium releases energy due to a nuclear reaction and TNT releases energy due to a chemical reaction. So we are essentially comparing the energy released by a nuclear reaction to the energy released by a chemical reaction. When you do compare the energy, you will see that 1 gram of uranium releases as much energy as 17,000 kilograms of TNT. Just imagine that. 17,000. That's quite possibly more than the mass of like 10 elephants combined. Forget about Athek Barata Rattarang. We are in the Athek Barata TNT league now. By the way, you might have noticed that in the reaction we discussed, a single neutron comes and hits the uranium atom, and that is what causes the reaction. But you might also have noticed that the reaction actually produces 3 more neutrons. So what if these 3 neutrons collide with 3 other uranium atoms? Yeah, that's right. They will cause 3 more reactions and produce 9 more neutrons.
Oh shit.
And this will spread like wildfire, and soon you will have so many reactions per second that the energy being released will be explosive. In fact, that is exactly how a uranium bomb works.
After falling for 43 seconds, the time and barometric triggers started the firing mechanism. A uranium bullet fired down a barrel into a uranium target. Together, they started a nuclear chain reaction. Solid matter began to come apart, releasing untold quantities of energy.
Alright, I think that's enough about uranium. Now we'll move on to to an example of finding the nuclear binding energy of an atom using its mass. Consider a helium atom. Now this is composed of 2 protons and 2 neutrons. So what you need to do is you add the mass of the reactants and then you subtract the mass of the helium atom, which gives you the mass defect. And then we again go through the motions of converting the mass defect into kilograms, and we plug it into the equation E equals mc squared, and you get the energy, which is the binding energy of the atom. Well, that's it for this video. I will be upgrading this video soon. This is just a stand-in to help the 2020 A-level students. And on that note, before we end, I'd like to talk about something else as well. And this is the wave nature of matter. You see, the scientist Louis de Broglie, or maybe Louis de Broglie, suggested that all particles tend to behave as waves as well, and that the wavelength of the wave that is formed by a particle can be found by comparing the momentum of both the particle and the wave. So a particle momentum is given by P equals mass into velocity, whereas the momentum of a wave is given by momentum P equals the Planck constant divided by the wavelength. So if you equate the two momentums, you can subject the wavelength, and this is called the de Broglie wavelength. I wanted to breeze past this topic because this is also something that is included in the syllabus, but it hasn't been seen in a while, so it's better if you remember the equations. Alright then, that concludes this video, and we'll see you next time. So cheerios, bye bye, tata, sayonara.